In this video, we're going to introduce the idea of local linearity for surfaces or functions of two variables. If we have a surface, what we can imagine is picking a point on the surface, and if we know some properties about the surface, in particular information about its slopes, we should be able to build a plane that is tangent to that surface, that just touches at that one point and shares the same slope information as the curved surface there. For consistency, we're going to label the point we're looking at x equals a, y equals b, and the surface or the z value is given by our function of two variables, f at a and b. Our goal is going to be to try to find a translation from what we know about linear functions in two variables and connect that back to what we know about slopes of surfaces with derivatives. If our goal is to write the equation of the tangent plane, first we start off with our function. So this is our curved surface. And then we consider the point slope form for a plane. It has a very simple form to it. We have a constant, and then we have another constant times x minus a, and a third constant times y minus b. And this, of course, goes through the point a and b. If x is a and y is b, we're actually going to have a c value for the z coordinate. So this is a plane through the points a, b, c. Let's back it up, it shouldn't be plural. So this is a plane through the point a, b, and z value c. If we're trying to associate these two pieces, we might ask what the slope of the curved function is in the x direction at the point a, b. Well, that is exactly what we mean by the partial derivative of f with respect to x at ab, or what we sometimes notate with the subscript x, what's the x partial derivative of f evaluated at the point ab. That's comparing or computing the slopes of the curved surface. If we ask the same thing of our tangent plane, well then the slope is simply this coefficient out front of the x, this m value. The slope of the tangent plane in the positive x direction is simply m. Going back to our picture for a moment, what we would like to have is, in the positive x direction, our plane to have the same slope as our curved surface. Well, if we know how both of these define their slope in the positive x direction, we can tie them together. We would pick m equal to the x derivative of our function of our surface at the point ab. And by perfect analogy, the slope that goes in front of the y coordinate, we would compute it by finding the y derivative of our surface at the point AB as well, and calling that n. And finally, if we want to know the z coordinate at the point AB, well, that's exactly the height that we should obtain from our formula. So we're going to have that last unknown constant c defined by the height of the surface at the point x equals a, y equals b. All of those calculations lead us to this next stage, which is a formula for the tangent plane. So if we want a plane that shares properties with the curved function, we're going to pick this coefficient here as our z value, what we called c, at the point. And then we're going to have our x slope and our y slope, or our n value here, as the coefficients of x and y respectively. Sometimes it's important to make the distinction. This is the formula for the plane, and notice it has an equal sign. The z on the plane is given by exactly this sequence of calculations. However, if we're using our tangent plane as an approximation, going back to our picture again for a moment, this plane is close to the curved surface and will be easier to work with computationally and maybe in other ways. So if we want to approximate the curved surface nearby that point, we would say that our curved surface f of xy is going to be approximated by the tangent plane. At this point, it's worth throwing back to what we saw earlier in the course, which was the single variable functions, where we had a tangent line, and that was given by y equals f of a, notice the parallel to f of a and b, plus f prime of a, well, that was a slope, times x minus a. So in fact, this is a perfect analog to these first two terms in the tangent plane, with the additional ingredient that the slope is now in a particular direction, the x slope, and then we add in this extra effect from the y direction. If we take steps in the y direction, it's mediated in terms of height through the y slope. As a quick side note, if we focus on the point AB, and again, we can imagine that being a point on a plane, if we talk about a point away from there and call that point the point xy, we can also imagine that x minus a is simply representing a change. How far do I go between x and a? And in the y direction, how far do we go between y and b, this direction here? If that's the case, sometimes it'll be helpful to bring this term over and use this alternative approximation, which is the same formula, simply rewritten. All we've done to accomplish that is to think of a change in x as being a base point A and then moving to some nearby x coordinate. The same thing for the y value. This is a difference between two y coordinates. And this delta f is the value where we are on the curve, and we subtract off the function value at the point where we are. Again, going back a page, all we're doing is taking this coordinate here, this value for the z, and bring it over to the other side. We get a difference. Well, that's a difference of f values, or delta f. Depending on the scenario, it may be more convenient to use this form or to use the formula from the last page. It really boils down to what we're trying to compute. Do we want to know how much is f changed by? In other words, how much have we gone up in our heights? Or do we want to compute the actual new height? What is the value of our surface at that new x and y coordinate? Again, both formulas have all the same contents. It's just a little different packaging, and it just might save you a step or two to use one instead of the other.